Hi everyone, welcome back to another chemistry video with Chem for Com or Chem with Com. Sorry about that. Um, all right, let's get going. So this topic is new, and it's going to be Lewis structures, bonding, and molecules. The specific subtopic is going to be, let's take a look. Lewis symbols, the octet rule, and ionic bonds. All right, before we get started, the secret word for this video is Rambo. So the secret word is Rambo. All right, so we're going to use something called Lewis symbols or structures. We use Lewis symbols to describe valence electron configurations of atoms and monoatomic ions. Basically, it's the symbol, and however many valence electrons we're going to represent with dots. So hydrogen, one valence electron, it's a dot. Helium, two valence electrons, two dots. All right, let's do lithium now. Lithium has three protons. I'm going to write that out. So three protons. It has two energy levels because it's in the second row of the periodic table. I was drawing it like this, right? But since we're only going to do the valence electrons, we're not going to worry about this or this. So it's going to be just lithium with a single electron. All right, and so that's how it's going to go. Um, and let's do a couple of these, and then we're going to kind of blast through this just to kind of show you. But remember this, we had hydrogen was one electron or one proton, one energy level, one electron. Lithium was three protons, two energy levels, total of three electrons. Sodium, 11 protons, three energy levels, one, two, and then we had one, two, three, four, five, six, seven, and eight. And we have one on the outside. Well, right, beryllium, the same thing. Remember, if you go back to the lecture, I believe it was lecture one, two, three, lecture five. One of those, either four, five, or six. You can go back and take a look. Periodic trends. So lecture five, right? Um, it'll show you kind of the whole thing that we drew out. But if you look here, if we look at the valence electrons, we have one valence electron for hydrogen, one valence electron for lithium, one valence electron for sodium, right? So again, this column is one valence VAL electron. This is two valence electrons. This is three valence electrons. This is four valence electrons. This is five valence electrons. Six valence electrons, seven valence electrons, and then here and below are eight valence electrons, where helium was only two valence electrons, right? So let's draw these out. Hydrogen, one valence electron. Lithium, one valence electron. Sodium, one valence electron. Beryllium, two. Magnesium, two. Boron, three. Carbon, four. Nitrogen, one, two, three, four, five. Oxygen, one, two, three, four, five, six. Fluorine, one, two, three, four, five, six, seven. Helium, one, two. Neon, eight. One, two, three, four, five, six, seven, eight. Chlorine, one, two, three, four, five, six, seven. Argon, one, two, three, four, five, six, seven, eight. But these kind of look similar, right? One electron, one electron, one electron, seven, seven, eight, eight, right? They are going to have the same number of valence electrons, right? So they might look similar, but what difference is the symbols. So make sure you pay attention to everything, the dots and the symbols. All right. Just a couple more, right? Sodium, one, magnesium, two, aluminum, three, silicon, four, phosphorus, sulfur, chlorine, and argon, right? Just again, the symbol and then the dots represent valence electrons only. Valence electrons only. All right. So draw the Lewis structure for sodium or Lewis symbol, just straight up sodium with one electron. Helium, right? Second, first row, two electrons. Phosphorus. So if you look at phosphorus, it's on column 15. That means it has five valence electrons. Calcium is in column two, group two. So it's going to be two electrons. All right. So again, octet rule is, we went over this before, but just to reiterate, main group atoms will form eight valence electrons, in which eight valence electrons interact with each nucleus. Counting bonding electrons is interacting with both atoms connected by the bond. And that's a lot of words, a lot of vocabulary. Let's come back to this and we'll explore these ideas without going through the formal vocabulary. But let's take a look. Eight valence electrons. So again, this is why we have ions, right? Hydrogen starts off with one electron and it can uh, gain or lose an electron so that it has a full valence shell. Actually, a better example would be something like fluorine because it's the octet, right? Let's do octet. Fluorine has one, two, three, four, five, six, seven. This is neutral. And this is an ion. It's a cation. Or sorry, this is going to be an anion. Anion is going to be a negative charge, right? Because this has seven electrons, but it wants eight, and that's the octet rule. So what happens is another electron comes in, and then it becomes F. It takes an electron from somewhere, from something, right? And now we have happy, right? Happy with eight electrons. All right. Again, um, main group atoms main group atoms will form structures in which eight valence electrons, and we'll say two, four, helium, He, with each nucleus, right? There's a nucleus inside fluorine. It's going to want eight electrons, right? Everything always wants eight. All right. So ionic bonds, when the things bond together, make ionic compounds. And this happens between a metal and a non-metal. The metal gives up electrons. That's what makes something metal, is if an element gives away electrons, that makes it metal. Everything that's non-metal will either share or take electrons. So we'll say share electrons or it's going to take electrons. So sodium is a metal, so it gives away an electron. Let's say it gives away an electron, so then it becomes 10 electrons, right? It starts with 11 as a neutral atom. Sodium doesn't mind giving up electrons, so it gives away that one electron only, so that it has eight electrons, right, in the valence shell, or a full valence shell. All right. So again, we're going to separate things into metals, and then here, these are non-metals. Let's draw that line again. Remember, hydrogen gets cut out, and then these are going to be right? These are metals. Everything else is non-metals. All right, metals and non-metals, that's how we're going to separate things. All right. And again, it's kind of to the left side here, and this kind of zigzags over. But these are the metals and non-metals. All right, I'm repeating stuff because it's important and it's easy to miss things. So, yeah. I don't know if I said this yet, but the word for this video, the secret word is going to be Rambo. So the secret word for this video is Rambo. All right, let me just scratch that off so I'll say it again. Okay, ionic bonds again happen between metals and non-metals. Metals give away electrons. So they're going to be positive charge, and that's going to be cations. That's why you see all these positives on the left side. Right? All right. Non-metals share or take electrons. So they're negative, and they'll be the anions. Again, we covered this before. It just we're talking about it again because it's relevant for this specific topic. Okay? Because we're going to bond metals and non-metals. We also have things called polyatomic ions. We covered this briefly before. Again, ions, right? That positive sign means it lost one electron. This here gained two electrons. This one gained three electrons, right? So, and there's not many positive ones, right? There's only basically two that we know of here. There might be a couple more, but there's not many. There's, I believe, Mercury has a couple positives, like a one positive one. But yeah, so polyatomic ions, we're going to revisit this, but these are ions, so they can contribute to ionic bonding. All right, so let's look at this. It says aluminum and carbon react to form an ionic compound. So metal, non-metal. All right, aluminum is going to be the metal, and carbon is going to be the non-metal. Predict which one forms an anion. So aluminum is the metal, loses electrons. So that's going to be the cation, right? Because of where aluminum is on the periodic table, we know it's going to be a 3 plus. Loses 3 electrons. All right, so then we're going to find carbon. In this case, it's a non-metal. It gains electrons. So this is the anion, right? And this would be a carbon. And since carbon can either gain 4 or lose 4, it's going to actually gain 4 because aluminum lost the electron. So this is, now these numbers don't add up, right? Aluminum can't give up 3 and then carbon pick up 4, right? And we'll come back to this and we'll actually do the correct numbers. Let's actually try it right now. Again, we're trying to make neutral compounds. So let's say aluminum and carbon got together and they reacted, and aluminum lost a bunch of electrons and carbon gained a bunch. So if we had aluminum 3 plus and carbon 4 minus, does that equal a neutral compound? A plus 3 and a minus 4, that equals -1. That's not neutral. Let's try 2 aluminums. Well, that's a plus 3 minus 4. So that's 6 minus 4. That's a plus 2. Not neutral. Well, let's try, let's see here. I already know what this is going to be, so let's try this again. Aluminum 3 plus, aluminum 3 plus, aluminum 3 plus, aluminum 3 plus, carbon 4 minus, carbon 4 minus, carbon 4 minus. That's going to be a plus 3, plus 3, plus 3, plus 3, minus 4, minus 4, minus 4. That's going to equal 0. Now, this is a pretty difficult one. I wasn't expecting you to get this far. What I wanted you to do is figure out this, right? So focus on that. But I want to do this just because Al4C3. Right? That's when you try to balance the charges and make neutral compounds, right? And again, don't worry about this. Don't worry about this part here. Kind of hard, do that one later, right? But this is the part I wanted you to know is basically find the predicted charges. All right. So ionic bonds, again, this is when metals lose electrons to the non-metals. So what happens is chlorine will take this electron from sodium. Magnesium will actually take both of those, or sorry, oxygen will actually take both of those electrons from, sorry, oxygen will take both those electrons from magnesium, right? But this is a little harder, right? This is saying there's 2 fluorine atoms, so it looks like this. 1, 2, 3, 4, 5, 6, 7. Fluorine, 1, 2, 3, 4, 5, 6, and 7. And I'll show you why we can do this. And basically what it happens is it takes 2 fluorines to take away the 2 electrons from calcium. So it ends up being CaF2 because there's going to be 2 fluorines. All right. So let's do a couple of these, but let's do some guidelines first. What you're trying to do is make neutral compounds, which means the charges of the ions should add up to 0. Now, here's where it gets a little tricky. You can never change the charge of the ions. I will say never. You can't ever change charge of the ions. But you can just quote unquote find additional ions with the same charge so that the charges add up to zero. Because if there's one atom around, let's say there's one carbon atom, there's going to be billions and trillions and quadrillions and moles of other carbon atoms. So it's not like we're making stuff out of magic, right? So if we're trying to make a sandwich, right? If you want to make a sandwich, can you go to the store and buy two pieces of bread and one piece of cheese? Okay, bread plus cheese, that makes a sandwich. But it's hard to go to the store and buy a single piece of cheese and two pieces of bread, right? You buy a loaf of bread. There's, I don't know, 20 slices in a loaf, maybe 25. You buy a pack of cheese, like the floppy orange cheese, that's what, 20 in a pack, right? You don't have to use up all of those, but you can make whatever you want from your ingredients, right? You're only going to take two slices of bread. Like here, we took two fluorine atoms and we had one calcium atom, right? That satisfies the neutral compounds part. So again, we're not just magically finding these atoms, they're there, right? They're available to use. We just have to use the right amount. So again, we're not magic, we're not cheating, we're not doing magic. You can just use additional ions with the same charges so that the charges do add up to zero. Let's try a couple of those examples here. All right. K is potassium. If you look on the periodic table, K has one valence electron. If you look at fluorine on the periodic table, it's seven valence electrons. Three, four, five, six, and seven. All right. So since this is the metal and this is the non-metal, right? The non-metals always take the electrons from the metal. What happens is these become ions now, right? This is K. It lost one electron, so that's now a positive. This is a potassium cation. This is now the fluorine anion. One, two, three, four, five, six, seven, eight. And it's important that now you put these brackets around fluorine because you want to show that fluorine took all of those electrons. So this is the anion. Now what's going to happen, as they do in chemistry or life in general, positive charges attract negative charges, right? This is now the attractive ionic charge. This is the attractive ionic bonds, right? So then it's going to look like this. K1 plus fluorine in brackets with all those electrons with the 1 minus. And the formula is KF because there's one potassium, one fluorine. All right, let's try this now. Lithium, again, there's one electron on lithium, Li2S. Let's pretend we didn't know what this is. We said we're trying to make something between lithium and sulfur. Okay, so lithium is one valence electron. Sulfur is six. One, two, three, four, five, and six. Okay, this is the metal, so it gives it up to sulfur. Well, lithium, cool, happy, right? Because it lost that one electron. But what's going to happen here, sulfur is not happy because it does not have eight. Sulfur still does not have eight electrons. So what happens is you have that lithium there that's a 1 plus already, but another lithium is always around. just like another piece of bread is always around, right? That's going to have the electron. Again, we didn't create this out of nowhere. It just, this is the formula to make this. So then it becomes lithium, 1 plus, lithium, 1 plus, and then now we have the sulfur. It has 1, 2, 3, 4, 5, 6, 7, 8. We have a 2 minus, right? And that's now a neutral compound, right? And so you can write it, right? These positive charges probably won't be next to each other, so it's going to look like this. Since these are identical now, you're going to write it as Li, two of them. Each of those has a 1. Um, I don't like the way they wrote that. So I'm going to do it my own way because I think it's more intuitive. Right, this lithium is a 1 plus, and it's probably going to be on the other side of this other lithium. This is a 2 minus, and then we have another lithium 1 plus. So the formula is Li2S. Again, let's do another one, but let's pretend we didn't know the formula. Barium and bromine. I haven't talked about naming yet, so let's just call it as bromine, like it looks like on the periodic table. But that's barium bromide, but let's take a look here. All right, barium. Let's see. It's on the second column, second group of the periodic table. It's going to have 2 electrons. And bromine has 7. 1, 2, 3, 4, 5, 6, 7. Well, yeah, bromine will take that 1. Cool. But barium still wants to get rid of last electron. So another bromine shows up. All right, this is the bromine that has the 8, right? And the barium is sitting around with the extra electron. That's still one that wants to get rid of. So I just draw it over here so we don't get confused about what electrons went where. And we can even make it different colors. Let's make this one green. That one's hard to see. Let's make it red. All right, that's the red electron here. And let's make this other one, I don't know. Can you see purple maybe? All right, purple. All right. But then another bromine comes around or is around, and it'll take that, right? It'll take that other electron. All right. So then we have 2 bromines and a positively charged barium. Well, the barium lost its, this is a 1 plus, or sorry, bromine is now a 1 minus. And so it's going to look something like this. It's going to have a barium that's now a 2 plus. We're going to have a bromine has 1, 2, 3, 4, 5, 6, 7. I'll draw the 8th one in a second. But then we have another bromine that's a 1, 2, 3, 4, 5, 6, 7. That's another 1 minus. I'm just going to draw these so we got the colors down, right? Because one of the electrons from barium went to the one bromine and the other electron went to the other bromine, right? So now we have 2. It'll look something like this, right? And we have to have the brackets, right? That makes it correct with the brackets. All right, so let's write it out. It's 1, and I'll draw the other red one in a second. I'm trying to color code things. 1 minus. And then we have our barium 2 plus. And then we have our right? This is going to be a 1 minus. So it'll look something like that. And then we have our, again, our red one there. And then we have our purple one. Just to show you, hey, they're actually different electrons, right? And so we have a little room there, but the formula is going to be barium, which is the metal first, Br2, BaBr2, right? Again, we gave you the formula in the beginning, but we can do this without knowing the formula because we know how many valence electrons they have, and then we know how many valence electrons they want, right? So you're going to have to kind of move your way around the information that way. All right, let's do another one. Predict the formula of the ionic compound, kind of what we just did, that formed between the sodium cation Na plus and the sulfide anion. We can do it, let's do it two different ways. So this is 1 plus, and then we have the S2 minus. Well, that's the same as a plus 1 minus 2. Where we're trying to form neutral compounds. 1 minus 2 is -1. This is not neutral. So because it's negative, we want to add another sodium to this. So it's going to be Na1 plus, Na1 plus, S2 minus. That's a plus 1 minus 2. That's going to be a neutral compound. So it's going to be Na2S. All right, let's do it the other way. Na with one electron. This is 1, 2, 3, 4, 5, 6. Well, sodium gives away that one electron, and it ends up being sodium 1 plus this sulfur, but it only has 7 electrons. It doesn't have 8. So another sodium is around. It could take another electron from sodium. So that now becomes Na1 plus, Na1 plus. This is sulfur with now 8 electrons. And that's now a 2 minus. So let's write it out. It would look something like this. 1 plus, 1, 2, 3, 4, 5, 6, 7, 8. 2 minus Na1 plus, or the formula would be Na2S. All right, either one. You can do either one. What's important is knowing how to create the formulas, and you know that because of those electrons. All right, predict the formula of the ionic compound formed between the lithium ion and the peroxide ion. And just to remind you, right, peroxide is O2, 2 minus. So let's do that. All right, so we have lithium. Lithium is a 1 plus. Peroxide ion is a O2, 2 minus, right? So that's like saying plus 1 minus 2 equals -1, not neutral. So we have to add another positive. So we'll say add, or we'll say solution, add another positive ion, right? So now it's going to be Li1 plus, Li1 plus, O2, 2 minus. That's going to be a plus 1 minus 2 equals 0. That's neutral. So I'll take the exclamation points off the other one because we don't have to be happy about that. We can put a sad face. All right, so now it's neutral. So there's two lithiums. So it's going to be Li2O2. That's now the formula for this lithium peroxide. All right, so the recap, ionic compounds, they're held together by ionic bonds, plus and minus charges. Ionic bonds are formed by atoms giving and taking electrons, specifically between metals, which give up electrons, and non-metals, which take electrons or share, right? And these ionic compounds, we'll get to this much later in the semester, but they usually come apart in water. We'll figure out why they do that later, but for now, that's it. All right, well, thank you very much. That's another episode with Chem with Com. We have two more topics for this specific, two more subtopics for this specific topic, and thank you very much. And I'll catch you next time.